The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody. Good afternoon. Welcome to the webinar. I'm still going to wait a few minutes for more people to join. I see people are logging in. We're about halfway the number of registrations. Now I'll give it one more minute and then we get started. I think we're good to go. I hope everybody can hear me clearly, can see my screen. Thank you for joining this webinar. So this is a webinar about the new heat release 2021.1. If you look at the history of the releases, we see that we have started in January 2018. So in the meantime, with June 2021, it took us quite some time to make this new release. The previous one was in October 2020, but we have had big new change now. So you will see there are many new features introduced. So that took us quite some time to implement all of these. Big thanks to all our developers at Comsof. So you see the results of the month's work that we have spent in this. A first new thing that you will see when you will install Comsof Heat is the new version of QGIS. So we have made the build package together with QGIS 3.16. So the previous version of QGIS was a 3.14, which was packaged together with the build. So now this is the 3.16. I will present the first part, and then about halfway, my colleague Julia will take over for the second part. I think most of you in the webinar are already active with the software, so this is not new for you, but I think also a few people in the webinar are new to Comsof Heat, haven't seen anything yet about what it is, what it does. So this slide, I have put it in here to give you a brief summary of what the software is doing. So it's a tool for district heating, network planning and design. We start from GIS input data, as you can see on the left side, street center lines, building polygons. We need on top of that, for the buildings, we need the energy data, energy consumption data, peak demands and yearly consumption. Then a set of technical parameters to configure the network. Technical parameters like supply temperatures, return temperature, pressure settings, velocities you want to limit in the pipes, these kind of parameters. Then unit costs for the pipes, for the substations, for the heat exchangers can be entered. And you can as well enter a number of parameters related with the operations of your network, such as the heat or cooling tariff, to calculate in the end not only a deployment cost of your network, but also look at the investment of your project and calculate values like net present value, internal rate of return, etc. So what does the tool do? It will generate a network topology. The topology generation is automatic based on optimized algorithms to interconnect the sources with the buildings in the area. The pipes will get the right dimensions. The network deployment cost will be calculated. And as I said, there will be an investment analysis of your project. So that's in a nutshell what the software is doing. We have already many existing possibilities and features, but with this release, we are introducing quite some new things. So what is new? First of all, the possibility to design two-pipe district cooling networks. You will also be able to design ambient temperature networks with two pipes. Heat pump can be used for combined heating and cooling. We are also introducing central and distributed thermal storage based on supply and demand profiles for seasonal or for daily storage. There are a number of features included for the increased accuracy in the network deployment cost and investment analysis. So you will see improved flexibility in the demand side equipment for single dwelling, multi-dwelling buildings. More equipment in the bill of material, T-joints, expansion loops, pipe joints, etc. And then a number of general improvements, as you will see later on as well. So let's start with the two new design strategies. What have we done? On the left side, you see the original existing design strategies which were there for district heating. So these three existing ones have been renamed into the ones on the right side. So you see that we have now district heating two-pipe for distribution, for transport, or for two-layer networks. And we have added two new strategies when creating the rules, one for district cooling for the distribution layer, and then one for low temperature district heating and cooling, so combined heating and cooling, two-pipe configuration in combination with heat pumps. So let's look at the first one now. The first new strategy is two-pipe district cooling networks. So I think you all know the concept of district cooling. Here we extract cold from a lake, from a river, and we want to supply the cold to the buildings that require cooling in the summertime. This means that the supply temperature is colder than the return temperature. What is also different than with district heating networks is the fact that the delta T is typically lower. That means that you will get bigger pipe diameters for the same power transfer. An advantage you have in these type of networks is that there is a lower temperature gradient with the soil because the temperature is lower. So you will require less insulation in your pipe systems. So what does it mean now or what has changed in the software? What do you need to enter to dimension such a network? It is very similar to district heating network. All the flow is quite the same, except for a few changes, of course. We have energy demand, which is now based on cooling instead of heating. The same principle is there, that you can define the cooling power in the building layer. When you create the demand points, the parameters will be copied from the building layer to the demand points layer. So you see there the attributes cool underscore and kilowatt, and then the cooling kilowatt hour per year, which is optional. For the dimensioning can be entered in the building layer or in the demand points layer. What we have done as well, to make it a bit more general, we had the heat source layer in the input project and the output project. This has been renamed into the energy source layer to make it usable for as well heating as cooling. And as you see on the right side, when there is a cooling source, it will be blue. Heating source will be red on the map. So how do you make the distinguishment between heating and cooling? So you edit the energy source layer. The identifier is a simple string you can use to identify the type of source. Here we have a river source, and the type here will indicate whether it's for cooling or for heating. So you can use a capital or a small case C, and that will also then determine the color of the heat source in the map, as you just saw. The default, when no type is present, is heating. So to create such a rule set, as shown before, select here the disti cooling two-pipe distribution layer. You will get a new rule set. And basically, you won't see a big difference with the district heating parameter set. Just know that here the supply temperature you enter has to be lower than the return temperature. For simultaneity, we have now a similar formula, which you can apply, or you can work again with your custom values as well. For cooling, yeah, you select here the space cooling demand. Of course, there is no similarity as in heating with sanitary hot water, so only the option for cooling here exists in the Dropbox. And currently, only supported for single sources, which will expand later on in future versions. Another small change is when importing pipe definitions, you still find the pipe libraries folder in the Comsof installation folder, but now we have split it up in cooling pipes and heating pipes. Some manufacturers have pipes specific for cooling, so we have put them in a separate folder. But of course, you can use as well the pipes for heating and cooling networks. Just know what to select. Series 1 typically has the lowest insulation, so these might be used for cooling networks. And then the output, also everything very similar, except that you will see now the simultaneous demand, the peak power for cooling with the _C, and the total cooling peak power for the area is indicated here. So we're looking at the distribution points. If you look at the distribution pipes, you see here as well the simultaneous demand for cooling that is being transferred with that specific pipe. And another difference is we don't have any heat losses in the pipe. Actually, because of the friction, we have a small gain in heat. So that is also indicated here. We have a small gain in heat, which is actually negative in this type of network because you want to use it for cooling. That is also calculated and indicated here in the list of calculated parameters. Okay, so that's the first topic, which is new. If you have questions, I suggest to keep them for the end. You can enter the questions in the chat box. We'll take them at the end. So then the next strategy is low temperature district heating and cooling networks with heat pumps. So just some background before we go into the technicals. So we have the traditional third generation district heating networks with a high temperature source, around 70 to 90 degrees, but you have very few sources available. So waste incineration, geothermal, CHP. When you go to the fifth generation networks, you're looking at low temperature sources with temperature levels around 10 to 25 degrees. And you get access to a vast range of new sources here, like rivers, lakes, sewage water, data centers, etc. The only problem is, okay, with 25 degrees, you don't have enough heat to heat up the buildings directly. So what do? We will use a heat pump in the building. So we will supply heat at a low temperature around 15 degrees. And with the heat pump, we will further increase the temperature to the desired level for heating in the building. So the return pipe has a lower temperature, typically for heating networks, of course. And suppose that we have a source at the riverside at 5 degrees. It's not yet enough to get to 15 degrees. So we need an additional heat pump in between the river and let's say, the entry point to our network. Of course, you can as well have another source, maybe data center, where you have directly 15 degrees heat available. In that case, you don't need to invest in a heat pump at the source location. So that's in heating mode. But the advantage is, of course, that you can use the same network as well in cooling mode. So the heat pumps in the same buildings can be used for cooling in the summer. The difference is that the return temperature will be higher than the supply temperature in this case. and again, we're flowing back the return temperature back to the river. So this is, in a nutshell, the principle of this type of network. So two-pipe system that can be used for heating and cooling in combination with heat pumps at the building site. And yeah, optionally, of course, a centralized heat pump next to the source if that source temperature would be too low. So the principle is as follows. So we place a heat pump inside the building. We extract a level of heat from the network, but that won't be enough. So we need to increase the temperature with the heat pump. So we extract power from the grid, but we also extract power from the electrical grid to reach the desired temperature level. So the COP factor will give you the ratio between the heat that you need inside the building and the electrical power at the input side. So you can specify with the software, as you will see later on, 3 COP factors, one for heating, one for cooling, and one for sanitary hot water. What the software will do is you have to specify at the input the heat demand for the building, and then it will calculate the heat required from the network and the electrical power required from the electricity grid based on the provided COP factors of the heat pumps that you are using. So what do we need to give as an input in the demand points? Well, we need to give as well heating and cooling demand, of course. So we need the peak power for heating, for sanitary hot water, the peak power for cooling, as well as the yearly consumption for heating and the yearly consumption for cooling. Again, you can enter these values in the building layer, and they will be copied to the demand points layer when creating the demand points. To create the rules, you select the low temperature DHC distribution layer rule set. You can define the cost of the heat pumps in different ranges. Here, let's say up to 50 kilowatts. This is the price, up to 100, up to 400. You can specify the price of those heat pumps here in the demands tab of the rules. You can specify the different COP factors for space heating, hot water, and space cooling here. So this is the default setting that will be applied for all the heat pumps. Further, you can specify the space heating demand and the cooling demand. If you wish, you can only select cooling or only select heating. That is also possible. And here we have then the simultaneity factors for heating and for cooling that can be entered in the same way as before. Then in the resulting network, you will see that there is an additional new layer present. We have the equipment layer here, and specifically the heat pumps layer. If you select here a demand point, you will find a heat pump on the demand point location, and it will indicate here the electrical power required from the grid for heating, for sanitary hot water, which is 0 here, and for cooling. So that is what you will find in the heat pump output layer. Now what you can do is you can specify different types of heat pumps. Those different types of heat pumps can have, for example, a different COP value, depending on type you're using, depending on the size, depending on the power. Here I have defined a type 2 heat pump. We use the attribute COP_ID in the demand point table. And here you can simply put a string, an identifier to list a new type of heat pump. You can import this in the rules. And as you see here, you can specify for this second type of heat pump a different set of COP factors. Plus also here, you have the possibility to specify a cost for the heat pumps, which is not depending on the power, for example. So you can choose the method I showed earlier, or you can use this method here for a fixed cost per heat pump independent of the power. And then, of course, all results will end up in the bill of material as well for each of the different types of heat pump that you have defined in the rules. So that's basically, yeah, in a nutshell, what this new strategy is doing. If you want to know more about it, tomorrow we are presenting in, yeah, still, let's say, the last parts of the Heat and Power conference, which is, let's say, ending now soon, but you can join for free by connecting to this link here, ehpcongress.whereby.com.roundtable at 10 o'clock Belgium time tomorrow morning, where I will present together with my colleague Joseph some results, a study that we did for a comparison of a third generation network with a fifth generation network by making use of this new feature here. So if you can take note of this joining link, you can just join for free to this webinar. It will take 30 minutes, no more than that. Then another big new feature that took us quite some time is dimensioning of thermal energy storage in the network. Here's an example of a network. We have a peak power of about 10 megawatts. We have multiple distribution substations of about 2 megawatts. And now assume we want to add centralized storage for the daily or the season variations. Centralized storage means that we're going to put a storage tank next to the source. Well, by means of doing that, we will be able to reduce the peak power. So we can reduce the peak power to 9, 8, or less megawatts, depending on the capacity of the storage. What we can also do, instead of putting a centralized storage tank, we can put storage tanks next to the distribution substation. So we could put that in each substation a smaller distribution storage tank. And the effect will be that we will reduce the peak power from the clusters, instead of 2 to 1.8, 1.7, 1.5, again, depending on the capacity of the storage. So I will go through a few introduction slides first to illustrate a bit more the concept, and then we'll see what inputs we need and what we can calculate now and do with this new feature in the software. First of all, if you look at the demand side, we have daily variations because of the occupancy behavior in the buildings. People go out, people come back in the evening, they turn on the heat, they turn off the heat during the daytime. But there are also season variations, of course, because the change in the temperatures outdoor between summer and winter, which are occurring over the year. So this affects the peak load capacity of your network. So that's on the demand side. Also on the supply side, you can have different types of generation. Here we see in the top graph, we have a horizontal line, which is the production profile, where the demand is showing this graph here. So we have a mismatch between the demand, which is constant, and between between the supply, which is constant, and the demand, which is varying. Here on the bottom, we see a graph from a production plant with solar radiation. So of course they have a peak in the summertime, and the demand has a low in the summertime. So there is a mismatch between the demand and the supply. So that's something that we can correct by using a storage tank. So we can correct the mismatch between supply and demand by making use of storage. Moreover, it's a surplus that we have in here in the summer. We put in a buffer, and we can use it, for example, during the winter, to reduce peak load capacity and to reduce the production costs. So what's the design process? We have a number of inputs. First of all, the heat demand data, of course. We will need the source profiles, whether it be seasonal or daily. The demand profile, as well, seasonal or daily. The storage capacity that you want to use will be an input. The storage losses, because every storage tank has a certain loss. The heat is slowly escaping. The delta T in our storage between the top layer and the bottom in the storage tank. And we also take into account the cost of the storage. Then we will calculate the impact of the storage on the network, and the impact, what do we mean with that? We will generate in the output, first of all, the source peak power that you require without storage. And then we will calculate the peak power that you will require when using the storage as given at the input, the given storage capacity. Plus as well, we will calculate exactly the storage capacity. Let's say because at the input, it will be a percentage, as you will see, and the output, we will get it exactly in megawatt hours. Plus also the cost will be calculated, because at the input, we will provide unit costing. At the output, we will get the actual costing for the size we need. So when you look at the storage cost, there are many different types of thermal storage. The ones you see here are very large ones, typically used for seasonal storage. Tank thermal storage, pits, aquifer, boreholes. What is typical for the cost, that is that the price is going down per cubic meter as the size increases. So as you can see here on this graph, it is reducing in cost as we go up in cubic meters, so as the size of the storage tank is going up. So we have introduced a table in the rules where you can model this behavior. So for smaller volumes, you can give a certain cost. For higher volumes, you can give a reduced cost, another cost. So there is an option to model this in the way you want in the rules as well. So depending on the size in cubic meter, another factor will be used to calculate the volume, and then with the price per volume. What also will be important is the delta T between the input and the output. So the storage stratification, here we have the hot layers on the top of the tank, cold layers on the bottom. We have a delta T below between the top and the bottom. So that's also an input that we require for the calculation. The heat losses, typically given as a percentage. Heat losses also typically reduce as the size increases, and it's a relation between the surface and the volume. So as the surface reduces and the volume increases, you get this reduction in losses eventually. So you can also enter in the rules, as you will see later on, the heat loss percentage of the type of tank you are using. We will have to enter the demand profiles depending on what you want to design for, seasonal or daily. You enter the type of profile you need. If it's seasonal, okay, you have 8,760 hours per year. If it's daily, you can give 24 values. The files for the profiles are in Excel or better comma-separated files. For the seasonal, we require 870,000 values, one per hour, or you can make it simpler than that. You can specify, for example, here as you see, one value, let's say, or per month, and then you indicate the number of hours per month. That works as well. Anyway, that will also be documented in a manual, how to enter the values for these profiles. The file format for daily storage is similar, but here the peak is 1, and we enter 24 values, 1 per hour. Also for the source, we need to provide the supply profile, which in this case is a constant generation profile. Those files, how do you take them into account in your design? Well, we go to the workspace folder, input, calculation inputs. There's a new folder now, profiles, where you can save the different profiles, daily, seasonal. And as you can see here on the right side, you can specify different types of profiles for different types of consumers. We have, for example, commercial, we have residential, we have tertiary, and you have the default profile. So you can define as many profiles as you need and put them in these subfolders. Then just make sure that the profile ID that you're using in the demand points, you can see it here, the profile underscore ID has an attribute residential here, and that will link then to the folder indicated here. So this name has to match to make sure that the files are correctly found. For the sources, similar principle. We have an additional folder, profiles of the source. And here again, the files need to have the fixed names, daily profile or seasonal profile, to be recognized. Okay, so now back to the process. What else do we need? We need to know the storage capacity. So I will explain with the model in Excel how we calculate the storage capacity. Let's first assume a calculation for a network without storage. Here we have here a generation of a number of megawatt hours per month, about 6,000 megawatt hours here per month, approximately the same every month throughout the year. So we have a constant generation profile. But the demand, of course, is not constant. Here we see during the winter period, we have a higher demand, and the summer period, we have here a lower demand. So here we see we have still a surplus. We always have a surplus, but in the summer, we have quite a big surplus. So that means that we have to dimension here our source for the peak in the winter, while we see that in the summer, we have way too much. So if we could buffer what we have extra in the summer and use it in the winter, we can work with a source that generates less energy. So that's what's happening here. We still have the same heating consumption. And here we have reduced the generation capacity from about 6,000 megawatt hour per month to about 4,400, 4,000 megawatt hour per month. So now this creates a deficit in the winter times, but we still have a surplus in the summer, as you can see. So now in the summertime, we will start filling the storage, and that is then shown here. We start filling the storage in the summertime until it is fully loaded, let's say after a full cycle. So now if we look at the total capacity of the generated power, of the generated energy from the source added up with the capacity of the storage, we see that there is no more deficit. We have a surplus at all moments in the year. So we have been able to reduce the generation capacity of the source combined with a buffer which is filled up starting in the summer. And what we generate in the summer is consumed over the rest of the year, and we have no more deficit when the year has passed. So that is the principle. If you look again to this graph, the question is, what's now the maximum storage capacity that you could install? Well, in fact, the maximum storage capacity is whatever the generation can, whatever the source can generate. See here, the green part is a surplus which is being generated in the summer, but which we actually don't need in the summer. So in fact, if we take that part, plus the storage loss, which we will have anyway, because there's no way to avoid storage loss. So if we take that part and we put it together in a buffer tank, that would be the maximum storage capacity dimensioned for this particular network with this demand profile and with this supply profile. So we need to know, first of all, what is the maximum storage capacity, because anything beyond that point makes no sense anyway. We can never fill it up. So we need to enter the storage capacity as an input in the calculation. Now, of course, in advance, you will not know how much megawatt hours that will be. So that's why we leave the option to enter a percentage of the maximum storage capacity. So you can enter in the rules either the value in megawatt hour, or you can enter the value in a percentage. You can say, I want 5%, 10%, 15% of the maximum storage capacity. And then you can see how this turns out and the result and what it delivers you in your design. Sometimes the size is specified in megawatt hours, sometimes in cubic meters. Here is the conversion formula to convert the storage size from megawatt hours to a volume in cubic meters. So now how to configure the capacity for centralized storage. When we go to the common page in the rules, first of all, we have to select here dimensioning method will be based on profiles. The previous method, which still exists, of course, will be based on the peak and simultaneity, but now we have to select based on demand profiles. Then we configure here, storage period will be seasonal. And then here, for centralized storage, we take transport level, because for centralized storage, we will put it on the transport layer. Storage capacity as a percent of the theoretical maximum, we enter it here. So I took 20% here in this example. We have a storage loss of 15% per cycle, and the temperature difference between the hot and the cold layer is 50 degrees. So you better take the same difference between supply and return as in your pipe network for these calculations. What will be then the output? You will be able to see the results in the transport points layer. First of all, you will get the actual demand, the simultaneous demand of the main source if it would have been without storage, 9.1 megawatt, and the peak demand after storage. So this has been reduced to 4.4 megawatt with a storage capacity in megawatt hour of 1,451 megawatts. So that is the output for centralized storage. Plus as well in the bill of material, there is now the entry and the price calculation for the storage tanks. For distributed storage, it is similar. We enter here the layer with storage is distribution. You can only have storage on distribution or on transport, so you have to choose where you're going to put it, on either of these. Here we say that we're going to use 90% of the theoretical maximum, so more than the 20 before. And again, the output will be not only for one point now, but for every cluster, for every distribution point. You will see now the actual demand, the new peak power required at the distribution point, and the storage capacity required at every distribution point in the network. Plus as well, of course, the results will be displayed and calculated in the bill of material. So then what can you do then as a designer? You can make a number of simulations with different storage percentages and yeah, look at the overall network cost. So there will be, of course, an increased cost once the storage percentages go up all the way, as you can see, up to 30, 80, 100%. The total network cost is going up. But somewhere you will find an optimum. And typically that optimum will be between 1 and 20%. So you never need a storage buffer with the full 100%, certainly not for seasonal storage. For distributed storage is different. It's also different for in-house storage. But for example, for seasonal storage, you will typically have sufficient 10-15% storage capacity. If you want to read more about the methodology and the case study, we have published an academic paper. This is here the link on the Energy Journal. So it's called Influence of Centralized and Distributed Thermal Energy Storage on District Heating Network Design. So this was made by my colleague Joseph Jebamalai. All right, so that is concluding my part. I will hand over now to Julia. Okay, you should be able to present now.
Yeah, just 1 second. I guess you can see my screen.
Yes, all is good.
And hear me as well, which is very important.
Yes, please start. Thank you.
Okay, good. Okay, so yeah, first of all, hi everybody. I see there are many familiar names here. For the ones who don't know me, I'm Julia Farasini, Kurt's colleague. I'm technical account manager for Comsof Heat and also part of the client experience team. I will talk now about the classification of the service connections costs depending of the building type. This is one of our many new features for this version as well. As Kurt said before, if you have any questions, you can just drop them in the questions box there, and we'll answer all of them after the presentation, okay? So the classification of service connection costs, this feature allows to differentiate costs of the service connections depending of the building type or connection type. So, for example, as you can see in the image, we have like a front yard, MDU, basement, these different kinds of buildings, right? So you can do this, you can differentiate them by using the demand ID attribute on the demand point layer to classify these buildings. Okay, so you can see it here. When creating the service connection trenches, the software will automatically copy these values from the demand ID to the demand points on the demand points layer to the subtype of the service connections. So you see here we have the building. So this, our service connection trenches, they'll also have the same ID as this one. So as you can see here, this is the attribute table of the demand points, and in the demand ID we have some examples with the MDU, the front yard base, and the front yard. So these attributes will have to be imported in the rules. So you can set the different costs for each subtype. This is done under the common tab of the rules. So as you can see it here. And you can enter any cost you would like for each subtype. So in this case, we are using the cost scaling factor 2 for front yard, 1 for basement, MDU 2.5. Yeah, but this is up to you. You can set any kind of attributes as well as any values you prefer. There is no limit of subtypes you can add. Okay, these subtypes will be with the associated costs will appear also in the bill of materials. So in this screenshot, you can see the result in the bill of materials. The service connection trenches have the correct costs and volumes according to what was set in the rules. Okay, so you see here, for trench and pipe, the N20, the basement, and the MDU. So it's all there under the service connection. The next new feature I'll talk about is the flexibility in the demand side equipment configuration and cost. So here I have different examples of building settings. Again, we have a basement, front yard, MDU. If you look closer, you'll see that they have these different settings. For example, for the basement, you can see, the substation type, like for example here, 25 kilowatts these are just example of costs, like 1,000 euros. You need the extra activation costs per building. For example, one pump that is also 300 euros, and per home, one energy meter that is plus 50 euros, which is going to be different as in comparison with the MDU case here. So we have, for example, already starts with 5 homes. So you see here that one energy meter is going to be 5 times this 50 euros. You also have an additional one heat exchanger that is again 5 times 400 euros. So you see that depending of the building types, the settings, they will be different as well. So now what you can do, you can actually configure these different settings in our software via the rules. Okay, so this can be configured here under the demand tab, and the demand ID attribute will be our identifier, which must be imported. So again, you needed to have everything set in the input data so we can import them in the rules. Once the identifiers that are imported, you can configure them accordingly. You can set the extra activation costs per home here or per building. Regarding the heat exchanger configurations, it will place a unit a unit of a size dependent of the peak power of the building. So as you can see, yeah, here I'm gonna show you afterwards. You can do the same thing for all the different identifiers. So yeah, in the slides you see we have the basement here, front yard, MDU, and you can set all the configurations here. Here there is an example with the MDU and also without identifier. So you will see when it's the case that you don't have the identifier, this is like the default values that will be applied for all the buildings, which yeah, they have this attribute not filled or equal null. While, for example, here in the front yard base, is already set a minimum of living units. You can set the costs, the material and the labor costs. The activation type is per home. And yeah, again, the maximum power, all these configurations can be set for each of them. Here is an example again with the MDU. So yeah, the max power in kilowatts is set here. Cost, materials and labors. Here you can set actually both activation type per home, maximum of living units, and also per building. So it's very flexible. Here is how it looks like in the bill of materials. So you can see the different costs and volumes as extra activation costs. As you can see here, for example, in the demand. So we have the basement, front yard, the heat exchanger. So this is all listed here. Here we have some examples. So for example, this example number 1, we have one building with 10 homes with one substation in the basement. The substation size will depend and the cost will dependent of the peak power. So yeah, we have these 3 settings here. 1 extra pump activated per building, 10 additional heat exchangers per home activated per home. The cost is 400 euros per unit, 10 extra energy meters per home. So yeah, in the second example, we have again one building, but instead of 10 homes with 5 homes. So you see, we can actually configure this now with a high level of detail that it was not possible before in the previous versions of the software. So as I say, this gives you a lot of flexibility to work with these different kinds of buildings with different demands and requirements. Another example, for example, one building, one home with a front yard. So we have this one heat exchanger in the building. The substation size cost again will be dependent on power. So if it's up to 25 kilowatts, it's going to be 600 euros, up to 50 kilowatts, 800 euros. One extra energy meter activate per home. And our last example will be one building, one home with a front yard, installation in basement. So we have the heat exchanger in the building, 1 extra energy meter activated per home, 1 extra pump in the basement activated per home. So this can be all configured via the rules. Okay. This new release also presents more details in the bill of material regarding extra equipment. So let's talk about the generation of this extra equipment in the network. Now Comsof Heat also generates T-joints, which are interconnections between these 3 pipes. You can define the cost per type in the rules configuration. There are also displayed on the map in the generated network, and the quantity is added in the bill of materials. So here you can see what I mean with displayed in the map is that in the QGIS view, in the GIS layer, you can also check, you can see where they are actually located in the workspace. Okay. And of course, in the bill of materials is also present. So in the rules file, you can set their costs under the common tab equipment. So I have here the common tab equipment, and we have here equipment type T-joint. And again, we can fill the new costs, the material and the labor costs as usual. In the QGIS view, there is a new layer called pipe equipment. So you can see the layer here. And you can see the T-joints are little X's, little crosses, yeah, in the map view. So yeah, if you would like to see them, to check the more information, like here I have the identify results just with the identifier tool to see their attributes and all the information about them. Via the attributes table, you can check their attributes in detail, such as type and identifier, which is actually the location between which pipes and branches the T-joint is placed. So it's here. So we can focus in this, what kind of equipment it is, T-joint, and where is actually located, what is the kind of T-joint we are talking about. In the bill of materials, they will be displayed as equipment with the correct costs and quantities. So you can see here how they are actually, shown in the bill of materials. There's a different, see here you have two different T-joints. I'm going to explain this in the next slide, but there are different types here. Now they are with the same costs, but we're going to change this in the rules and then see the updated bill of materials, how they look like. So here in the rules, you can set these different kinds of T-joints. You must just add the main pipes and branches where the T-joint must be placed, and also the material and labor costs. Once this is set, the software will place the equipment in the network according to what was specified in the rules. So you see here that we have now these different prices for the different T-joints, okay? So now you see, after recalculating the workspace, the updated bill of materials will show, the updated prices, the costs as well, and the volumes that were used. Okay, so it's all set in the rules, and then you can check the results in the bill of materials. Another new feature is the placement of expansion loops. The principle in the software is the same as for the T-joints. You will specify them in the rules and they'll be displayed in the QGIS view and also in the bill of materials. So the software will install expansion loops at fixed distance intervals. The user must specify the cost per expansion loop, and those additional costs will appear also in the bill of materials. One thing that is very important to mention is that this does not include any mechanical stress calculations, okay? So you have here, we're gonna set them in the rules. We can actually see them in the GIS layer and in the bill of materials, and that's it. In the rules window, you can set the expansion loops on the distribution and transport page layer. So the user must specify the distance between the expansion loops in meter and also specify the cost as a multiplier of the price per meter for the type of pipe. So you can see here that, you can check this option to place the expansion loops. And for example, here to specify the cost as multiplier of the price per meter of that type of pipe, we have an example, a DN100 at 1,200 euro per meter with a multiplier of 5 will result in a cost of 6,000 euro for the expansion loop. Okay, so you needed, to take a few things into consideration when actually putting this multiplier here to get the results that you actually want in your workspace, in your project. Okay. So you can visualize the expansion loops also under the pipe equipment layer in the QGIS view. So the same as the T-joints, you go here, you can see here is actually selected, that's why it's red, but you see that the type is expansion loop. Okay. And in the bill of materials, the expansion loops, they'll be also displayed as equipment. And here in the screenshots, you can actually see again the different types and the amount of expansion loops that were placed in the workspace. Another new feature is the placement of pipe joints to interconnect long sections. So this means that a joint will be added to a pipe segment whenever the default length of the pipes is not sufficient for the whole segment. So here we have an example of 6, 12 meters. This is usually useful when working with the steel pipes. The additional costs will be also present in the bill of materials. So in the rules here under the common, you can actually specify the default cost of a pipe joint. So you have here equipment type, pipe joint. In this case, we have the new cost, 200 euros per material and 8 euros for the labor. The user can also decide if he would like to actually count the number of pipe joints needed by checking an option available both for distribution and for the transport layer, which is this option here. This option can be enabled independently. So maybe you just would like it to have it for distribution or for the transport. So it's up to you to choose. Once this checkbox is enabled, another option will become available. So the segment lengths. This one can be edited also by the user. So by the screenshot, you can see the different segment lengths that can be added. So we have it here for the DN32, 6 meters, 12 meters. You can add way more for the bigger diameters, for example, DN300, 6, 12, 16. We are also very flexible. You can add what you prefer in this section here. Another example here is using the plastic distribution pipes. So on a 100 meters drum. So yeah, for example, all of them, they have this 100 meters. So this is also possible to configure. The results, they can also be checked in the bill of materials, and they're also listed under equipment. So you have the pipe joint here, the material cost, labor cost, total volume, the same as all our other features. In the common page of the rules, you can specify the different kinds of pipe joints according to the pipe type. So the material and labor costs can also be added, of course. So here, for example, would like to have it for the DN20, DN32, then you can just add via this plus button or exclude then afterwards. So the updated results will be shown again in the bill of materials. We saw it before, but now we changed the costs of them. So you'll see that is different depending on where they're actually placed. The last feature I'm going to present today is the split trenches on boundaries. So as you can see in the slides, natural and human created obstacles can be now added to Comsof Heat Designer via the boundaries layer. So that is this layer here in our input data. This functionality was implemented thinking of the extra horizontal drilling costs when encountering such obstacles. So the costs for the segments on those intersections can be set in the rules. As you can see here, I have like a railway, a waterway, a major highway. These will be our obstacles. And we would like to add these different costs when we have such intersections here with the trenches. So we're going to see this more in detail in the next slides. How it works, the subtype attribute from those boundaries will be copied to the intersection points of the possible trenches. They will also be in the bill of materials. And I'm gonna just go to the next slide. Here, so you can see our Comsof toolbar where you can actually find the split trenches on boundaries. Here you usually have the button to create the trenches. You just click in the little arrow and then there you have it. This feature is also useful for more accurate cost estimation. As I said before, horizontal drilling is way more expensive than regular trenching. So it's very nice to have this option to configure this in the rules now. The possible trenches will be cut up at intersection with a boundary. So certain attributes, they must be set in order to make this feature work. For example, you need to have the width attribute that will give the specific length for the creation of this smaller trench segment. And of course, the subtype attribute which will define that what is the type of the boundary actually. The costs, they will be assigned depending on the subtype attribute in the rules. Here you can actually see a screenshot of how the possible trench is created after the split of the boundaries functionality. In this case, I have the waterway subtype. So you see here that the possible trench is just like cut. I used the width of 4 meters here, so we have 2 meters for each side. But yeah, you can configure it any way you wish. Yeah, so the different costs, they can be defined in the rules as well. You can see here I have 3 different costs for the different subtypes. Oh, I'm gonna go back there just a bit. So for the waterway, I put the relative cost of 20 euros, railway 18, major highway 25. Again, you can add as many subtypes as you want, and also just change here the costs. In the bill of materials, you can see how the segments they are counted as well. So you see here, like for trench and pipe, in this case, the N25 for the major highway, you have here the labor cost, the total, and the volume. The volume is in meters. It's according to the unit of your workspace. Okay. So that's all for the new features. Now I'd like to talk a bit about the upgrade to the 21.1. For the clients who already have the subscription, they should receive it this afternoon, our version 21.1. Our developers, they are currently working in a bug fix release, which should be available in the beginning of July. So it's up to you to install the release that I'm sending you this afternoon, or to like to wait, for example, for the bug fix. Okay, so you should download it. It's up to you if you'd like to download it already today, this afternoon, or wait till beginning of July. Okay, so now I'm gonna pass it back to Kurt. I appreciate your attention.
Okay, thank you very much, Julia, for the overview. There's one more thing. Let me share the screen here. Okay, can everybody see my screen? Julia, can you see my screen? Can we all see the screen? I hope so. If you can, please go to the poll on the website. Okay, let me share the poll. There are just a few questions which I will activate. So the first question I have is, which of the new features do you like the most? So let's hope this works. If you can connect to the site, you can share your votes, and we should see the results coming up on the screen here. C&D, thermal storage, some people like them all, very good. All right. Then we don't have a clear winner, but we have thermal storage, the heat pumps, and some people like them all. So that's not bad. Next question is, which of these features you think you can use immediately in your projects? You might like the features, but can you use them? Okay, some people can immediately use thermal storage, cooling, extra equipment. Thermal storage seems to be the winner. And combined with the extra equipment and the bill of material. Nice. Okay, one more question. A bit off topic. Who will win the UEFA Cup 2021? Please show your votes. Country with the NATO headquarters, a country north of France, a country south of the Netherlands, but it's looking very good for Belgium, I can see.
Yeah, nobody's voting for the capital of Brussels.
No, too bad.
It's not gonna win, no?
No. Well, that concludes the release webinar. I don't see a lot of questions here in the chat. So that means that everything was very clear. Thank you all for joining the webinar. There will be a recording if you'd like to rewatch it or send it to some of your colleagues in the company. So you will get an email later on, probably tomorrow, with the link to the recording. And if you have any specific questions, just contact me or Julia. Also, there are quite a few new things in there. For example, the storage, the heat pumps. If you need some help with configuring everything, give us a call, contact us via the support. Possibly we can help you configuring all the parameters in the software to do it in the right way.
Yeah, Kurt, there are some questions.
I don't
know.
Can you read them?
Yeah, I can read them. People are asking if they will have access to the slides. So yeah, all of you, I think everybody who registered today, you'll have the recording, right, Kurt?
Yeah, and
of
we
the
can
session.
send as well a PDF with the slides, yes.
Yes, the slides, and also there was a note from Frank about the just a remark about, now he left, but he left a remark about the water temperature from the rivers, that even during summer it should be higher than 5 degrees. I mean, from your slides that you mentioned there, that but it was just a remark. I mean,
correct. All right.
That was it, and lots of thanks to us. And wait, because I can only see very small as well. I'm trying to make it bigger so I can read the questions. Okay, so I'm going to read this for you, Kurta. How is the current heat loss in a standard heat network calculated? And how much with the buffers influence the heat loss of the network?
Yeah, the heat loss is currently calculated based on the formulas in the EN 1396, I don't know, standard. And now with the buffering, well, the principle remains the same. I mean, we have the heat transfer running through the pipes. We still apply the same formulas, which are actually part of our training. And as indicated, the additional losses that we will have now is the buffer tank storage throughout the year, throughout the day, which is given by a certain percentage. So that is then extra capacity that is needed in the buffer. So I don't know who asked it, but you can refer to the training. And the training slides, we explain it in all detail, what standard is used, what formulas are used to calculate the pipe losses, the heat losses in the pipes, I mean.
Yeah, I think if I'm correct here, it was Mark van Oostende who asked this question, if I can see it here. I think that's it with the questions. So if someone still has a question, now is the moment to ask. Otherwise, of course, you can always contact us via email afterwards, Kurt or myself, and we'll be glad to help also with the new features. If you have any difficulties or any doubts, you can always reach to us.
Okay.
Yeah.
Thank you very much. Then I will close the session for today. Have a nice day and see you later. Bye.
Okay. Thank you all. Bye.